Hello, guys.
Yeah, Krish.
Hey, Christian. I did get your email. I didn't get a chance to respond.
Oh, that's okay. Yeah. Sorry.
Yeah, let's talk about it after the class. You're misinterpreting the whole thing. I need to
Okay.
tell you very straightforwardly.
Okay.
Yeah. So let's talk after the class. That's the best. Yeah.
Okay.
Okay. Jeremy.
Hello.
Okay. What was here? Oh, Matt is here today. That's nice. Okay. I graded the exams and posted it. Hopefully you got a chance to see it. So when I post it, do you guys get to know that I posted it? Is there any information you get, or how does it work typically?
Yeah, I get a notification.
Okay. So here is the distribution as of now. So coming to midterm 2, the top score was 100, full score. And then there was a 95, there was a 90, an 84, 80, 76, and 57. 7 of us. Coming to, so this is midterm 2. If you go by the total, the highest score for now is 98. This is before curve, 98, 96, 90, 86, 69, 64, and 60. And there is this curve, what is this, quizzes, right? Decide how much of the curve parameter you get. So this is 0.911, 0.91, 0.4, roughly like that. And after you curve it, so what I decided is so the curve parameter, I gave back 15% of the points that you lost. That's what I returned. Remember, that's the only parameter I decide on based on the class. And this pretty much stays the same, I guess. At 97, 92, 88, 74. Okay, so that's the class distribution. If you have any concerns, so this is midterm 2 is over now. A good bit of grades are collected. They have homework remaining, and there's a final exam. So typically, at this point, if you keep doing whatever you're doing, you will be able to maintain your grades. So that's A for sure. And there's B, C. So that's grades. If I So what's remaining, we have homework 8 and we will keep going. I think there are 4 weeks remaining, so we can do about 4, surely 4 homeworks, maybe more if possible. So that's Monday. And final exam, which is pretty away at this point. This is actually this is on the first day of the finals week. It's on a Monday. Yeah, it is on the first day, but not the first hour. And it is at 2:40. Do check for me, one of you guys, whether I got this right. At least once I have made this mistake, so it helps to have a check. Any questions in general on logistics or anything? Okay, so let's proceed with what we were doing. We call this relative kinematics. Relativistic. It's like saying that, remember, when you do Newtonian physics, first you talk about what if there was no force acting on a system, given an acceleration, what can you talk about the system? Or what can you talk about the motion of the particle? And that's what we are doing here. We have learned, based on Lorentz transformation, that there is a quantity negative of a invariant distance we have been calling, which is basically minus c squared dt squared plus dx. You can say this is dx dotted with dx, right? If we are working in just one dimension, then this is just dx squared. This was based on the idea that we said if we have with respect to the origin, z squared minus c squared t squared, that comes out to be a constant. Since Lorentz transformation is a linear transformation, if z and t satisfies this, the change in z and change in t also will satisfy that. That's a property of linear transformations, and it can be a finite difference or it could be an infinitesimal difference, and everything is fine with that. He then said that if I were to take this common outside, I can define 1 plus or minus, right? And if dx is the displacement of a particle that is moving, then that becomes the velocity. So we recognize that if this is the position of a particle, this is nothing but velocity. And beta could be v over c, right? That's the notation we started. And in terms of this, then we have minus invariant distance squared times minus c squared dt, which is the time measured in that frame, an infinitesimal difference in time. And this is 1 minus beta squared. We also defined gamma to be 1 over 1 minus beta squared. And often this is called the Lorentz factor. So in terms of the Lorentz factor, then I have to take this to the left-hand side. I can get rid of the negative sign. So this is gamma squared ds squared equal to c squared dt squared. Or often this is just written as ds is equal to c times dt. We will use this a lot in our discussion today. So a time, an infinite, or time itself, like since it's a linear transformation, time is related to the invariant distance with the factor of gamma. And this is the time which actually decides how the particle is moving. Okay. Any question at this stage? Now the idea is that anytime we take a derivative, remember that to define our velocity and acceleration, we need to take a derivative, but we don't want to take the derivative with time. Instead, we will take the derivative with respect to this invariant distance and use that to find new quantities or the invariant properties of velocity. So that's going to be our goal. So we already defined what is a 4 position. 4 position is x alpha, where alpha can run from 0, 1, 2, 3. So this is x0, so this is ct, and the vector x. I should actually tell something about unsaid notation here. So whenever there are Greek symbols used, alpha, beta, the mu, nu, and so on, that's understood that it runs from 0, 1, 2, 3. Either from 0, 1, 2, 3, that's what we are doing in this class. Sometimes there are books that run from 1, 2, 3, 4, and the 4th index is associated to time, right? Either way. If instead you use Latin indices, I, J, M, N, then it is understood that it runs from 1, 2, 3. So the space for uses Latin, and the Greek letter is space and time. Again, this is commonly used between almost all the modern authors. Like I would say in the last 50 to 70 years, whatever books are written uses this. That need not be, that's not a necessary rule. You should always make sure that that's what is. Here, what I do is that x alpha is x0 and x1, x2, x3. x1, x2, x3 is being written as a vector, and x0 is being written, the 0th component is written as time. That's the notation I'm using. Once you know what is being written, then it's okay. So that's your 4 position. And remember, if that's your contravariant 4 position, if I want to write covariant 4 position, I just put it downstairs and put a minus sign in there. So maybe just highlight that once. So x alpha would be equal to minus CT. So notice the procedure here. Whenever I'm going from contravariant to covariant, or for that matter from covariant to contravariant, I flip the sign of the zeroth component and keep the rest of the three components the same. Right? That will be our procedure. We discussed this before also. And just one more. Oops, I think I can too far. One more point is that the invariant quantity associated with 4 position will be got by multiplying these two, which is in our notation, just multiply these two with the negative sign. Okay. If I'm multiplying these two, just get the negative sign also. And this is minus c square t square plus x dotted with x. Multiply this with this and then add the rest of it. So that's what we have already introduced. Okay. That's good, but now we want to introduce what is called a 4 velocity. Remember, again, I should caution you, velocity remains velocity. The physical velocity that we associate with a particle stays the same as Newtonian physics. It doesn't change. But we are just constructing something called a 4 velocity out of that. So what is going to be the definition of 4 velocity is going to be u alpha. So it's going to be a 4 vector, as you can see. This is going to be dx alpha. Take a derivative with respect to ds, the proper time, not the normal time. Take it with the proper or the invariant distance, not with the time. The dimension of s is not time, correct? So that's not convenient because if we are defining something related to velocity, it should have the dimension of velocity. For that purpose, just multiply it by c. That's a distance over a distance, that's dimensionless. Multiply it by c, and whatever this quantity is going to be having the dimension of velocity. So what is that equal to? If we are doing this, each component has to be, we have to take the derivative with respect to ds. So let's do that. So this is the same as c is sitting outside. There's already a c there. So that's c dt over ds and dx over ds. Okay. Notice that x is a function of time. So if I want to hit it with time, if I'm taking a derivative with s, I just have to do a chain rule. So let me use that. So this is equal to, put that inside, that's c square dt over ds. And the second one is there is a c, I'm going to use a chain rule, dt over ds and dx over dt. I do that so that I get back my velocity there, right? dx by dt is my velocity as measured in the frame I'm in. I'm having only one frame at this point. Right? We are not going from one frame to the other frame. This is all happening in the lab frame if you want. That's velocity. And remember the first relation that we wrote in the beginning of the class, we said that if I were to write it here, gamma times ds is equal to c times dt. That gives me gamma to be equal to c times dt over ds. So I can replace dt over ds with gammas everywhere. So that's where the Lorentz factor shows up everywhere. That's basically just the derivative of time with respect to the invariant distance. So then this becomes, so 4 vector is c times gamma, and gamma times velocity. That's your 4 vector, whatever that is. Like, as I said, velocity stays velocity. That's your velocity. But now velocity and the Lorentz factor and the speed of light c, they all together construct what is called a 4 vector, and they have some transformation properties. Okay, so what kind of transformation properties they have? If we want to take the zeroth component and the space components, they all transform under Lorentz transformation exactly like position and time. But what is more interesting is to find out what is invariant. Right? When we had position and time, we found that the scalar product between them is invariant. So we are always interested in the invariant quantities, not the individual components. We don't care for this velocity, because if we measure this velocity, if I compare it with another observer, they will measure another velocity. So it's not very useful. So the invariant quantity is more interesting. So let's measure that quantity. Measure, or let's calculate that. So U alpha, the contravariant for velocity, is c times gamma, and velocity times gamma. What is covariant for velocity? I just flip the sign of the zeroth component of the vector and keep rest everything the same. So hopefully my gammas are not confusing with velocity v. So that's one is velocity v and one is gamma. Is that clear? Any confusions as of now? Yeah. So that's your U alpha, U alpha. What is the invariant quantity associated with this for velocity? Remember, this quantity will be identical for every frame. Whoever measures this, any person going relative to each other, they will all measure the same quantity for this. So that's interesting. We would like to know what that is. So let's multiply these two. So remember again, how do we calculate this? Multiply these two and then add that to the product of the rest of them. So that's minus c squared gamma squared plus v dotted with v and gamma squared. V dotted with v is v squared. So let me pull out minus c squared. In fact, let me pull out minus c squared and a gamma squared. And I have 1 minus as a v squared over c squared, which is nothing but beta squared. So this is nothing but beta squared. But what is gamma squared times 1 minus beta squared? Gamma squared, remember, is 1 over 1 minus beta squared. So when I multiply these two, that's 1. So this is just minus c squared. So what is the quantity associated with velocity that will remain the same? It's not too surprising at this stage. That is the speed of light itself. Right? If you measure speed of light in one frame and measure speed of light in another frame, that remains the same. Right? That's how we began the whole process. Remember, Lorentz transformation assumed, or principle of relativity assumed that speed of light remains the same, and that is how we reached here. So this is not very surprising, but now we know at least that this is the time piece associated with the velocity, and that Lorentz factor plays an important role. What's the role of the negative sign? This is okay, there is a negative c squared, but what's the role of the negative sign? Any comments on that? if you have a quantity, invariant quantity that is negative, what does that mean? In the space-time diagram, or let's say in the Lorentz transformation?
It means it's time-like, right?
Yes, this is a time-like vector. That's good. Right? So that means this is time-like vector. We can conclude something immediate before we proceed, right? And that is that if that's a time-like vector, remember what is perpendicular to a time-like vector? I think that was asked in the exam also. Like if you have a space-time diagram like this, any vector that's say in this cone is time-like. If I ask what is perpendicular to that, that is necessarily space-like. It will be here. So time-like and space-like vectors are perpendicular to each other. Okay. So, but why is that relevant here? So let's see. First of all, before I proceed, we won't talk too much about acceleration here. So next step will be I define for acceleration, right? So that's for acceleration. So this is for acceleration. And that will be defined as derivative of for velocity with respect to the proper distance, which is c, right? And multiplied with c for the dimensional reasons, right? That's okay. We want, I mean, we can discuss a lot there itself, but with time constraint in mind, let me not go there too much. But one thing we can immediately conclude without spending too much time, and that is the following. Let me start with the invariant quantity associated with velocity and take a derivative there. Take the derivative of that expression, and I learn that I can hit the first velocity or the contravariant velocity with that, or I can hit the covariant velocity with the proper distance derivative, and c square is a constant. So it doesn't depend on time, and thus it doesn't depend on any distance either. So that's equal to 0. This is our, if I multiply by c overall, that's acceleration. Plus u alpha times a alpha is equal to 0. These two are the same, whether I multiply a contravariant with a covariant or a covariant with a contravariant, it doesn't matter. So it's 2 times that, that is 0, which means that u alpha times a alpha is equal to 0. Which means that acceleration is perpendicular, the for acceleration is perpendicular in the Lorentz sense perpendicular. So for acceleration is perpendicular to for velocity. And one can prove this in more different ways, and which means that the for acceleration is space-like. Okay, velocity of a realistic particle, because it goes slower than speed of light, is a time-like vector, and acceleration is a space-like vector. And we won't talk more than that for acceleration. So let's go back to velocity and see what we can do. And as of now, nothing has changed, right? As of now, what have we done? Like we realize that there is Lorentz transformation, which keeps something invariant. We define for position, but just it's in principle irrelevant because position and time, we just learned some quantity that there is an invariant distance as far as Lorentz transformation goes. We define for velocity. No physics has changed yet. Velocity is velocity. Position is position. Time is time. Everything has remained the same. And now the next thing I'm going to do is what is going to make the change. So now we say that we define a new quantity. So let's say for momentum. So this is what Einstein did. He changed the definition of momentum and energy. So for momentum will be defined as P alpha will be just mass times the for velocity. As of now, all fine, should be straightforward. U alpha we know is C times gamma, right? And the other one is velocity times gamma. Okay. That is all fine. Remember your Newtonian energy. So energy Newtonian, so I'm going to call this Newtonian. Newtonian energy, how much is the Newtonian energy of a free particle? There is no forces acting on this, no potential energy. What's the kinetic energy associated with a free particle? It's half mv squared. So that's half mv squared. And if you want to write it in terms of beta, so it is half mc squared beta squared if you want. And what is the momentum associated or momentum in Newtonian physics? That's mass times velocity. These two is going to change. Okay? So what Einstein realized is that this actually is your energy and momentum. So this is not equal, so this is physics. This is, he postulated this. If you ask what was a big contribution of Einstein, was to see this connection. And he defined this to be energy and this to be a momentum. Notice this has changed now. Momentum is no more your old momentum, it is mv times gamma. But momentum and energy do not have the same dimensions, correct? So they're off by a velocity, so you have to provide that. So there's a C. So our new energy would be, so this is our, so Newtonian energy is gone, like we do, that's why I wrote it with a subscript, because I won't have to write it again and again. Whenever I don't write a subscript, I mean the new definition, or you can say the correct definition if you want. So this is mc squared times gamma. Right? Gamma, remember, has velocity in it. So this is mc squared over 1 minus v squared over c squared. Right? That's your energy. It is convenient to write it in this form, but if you want to see it explicitly, it is mc squared over 1 minus. So kinetic energy, which was half mv squared, is actually this. So let's see that more closely. And what about momentum? P, which was just mv, is now m times v times gamma, which is mass times velocity divided by 1 minus v squared over c squared. Okay. before we do anything, we should ask, okay, so now energy and momentum have become pieces of the same coin, right? It's like position and time. They have a role to play in Lorentz transformation. There is some invariant quantity related to that. And momentum and energy similarly seems to have something common. So what is it that is invariant between momentum and energy? So apparently if I square the energy and square the momentum and subtract it, that should be invariant. So let's see that. And for that, and before we'll come back and discuss it. So, or one should ask the question here right away. Maybe I should answer that and then proceed on to the next question. So, because it is too striking that where is the kinetic energy in here? Right? This kinetic energy has changed its form too strongly, correct? So, how do you see that connection in there? And that will have a hint of how things are going to go. Also, let's start with energy expression and see that this is mc square over 1 minus v square over c square. And we also roughly know that as the velocity gets smaller and smaller, we are better off doing Newtonian physics. Like this gets more and more accurate. So in what sense do we do that? Let's expand this. So for velocity very small compared to speed of light, that means v over c is very much less than 1, I can expand this as a series, a binomial expansion if you want. This is equal to mc square times 1. There's a minus half there. This becomes plus 1 by 2 v square over c square plus, if you want, 1 by 2, 1 by 8, right? So the next term is 1 by 8. There's a minus 1 by 2, minus 1 by 2, minus 1. I think it's 3 by 8, right? Minus 1 by 2 minus 1 is 3 by 2. And there's already a 1 by 2, 3 by 4, and there is a 2 factorial. So it's 3 by 8 v square b raised to 4 over c raised to 4. That's not important. We don't need that expression. And it keeps going. But if the velocity is small compared to c, let's think of 1 meter per second. Right? 1 meter per second over c, which is 10 raised to 8 meters per second. That's a 0, or that's a 1 after 8 decimals. If I square them, that's a quantity which has zeros up to 18, sorry, up to 16 decimals. So a very small quantity. And this will be much, much smaller. That will be 32 decimals. So I can easily ignore one of them. But now let's expand this. Let's see what this is equal to. This is mc square. And the second piece, notice the c square cancels out. And that's what your kinetic energy is. If you want, the next term is 3 by 8 m v raised to 4 over c square. There are two things. So energy is no more purely kinetic energy. The interesting part is that just because you have mass, you don't even have to move. Right? We usually associate kinetic energy with velocity. That's the definition of kinetic energy, actually, that it is associated with motion. But now the way energy is defined in relativity is not just due to motion. Just because you have mass, there is a energy associated with it. So this is called the rest energy. That means even when you are at rest, you have an energy associated with or energy associated with it, and that's mc squared. And that's kinetic energy if we want, that's your Newtonian kinetic energy. And that leads to the idea that if there is energy associated with mass, if you change the mass, you can release energy. And that's the idea of atomic bomb right there. Right? Very nice idea, but of course it leads to horrific things. But just if you change mass, anything that has a mass has energy associated with it. Let's go back and see. So energy and momentum has become pieces of a 4 vector. So what's the 4 or the invariant quantity associated with it? So let's calculate P alpha, right? So let's say P alpha is equal to, remember here, let's see, how should we do this? This was MC gamma, and this was MV gamma, right? Like it's kind of clear what this is going to be because P alpha is M times U alpha, right? So mass times the 4 velocity gives you this. So since I know the invariant quantity associated with the 4 velocity, I can kind of guess what this is, but let's do this anyway. So the momentum covariant vector associated with momentum is minus MC, and we have MV. So the scalar product associated with for momentum, multiply this out, so that's minus M square C square gamma square, and this is plus M square V square gamma square. That's equal to minus M square C square gamma square 1 minus beta square, which is 1. So this is minus M square C square. This can be written as, so what we have seen is P alpha is equal to minus M square C square, which is just saying that mass is the quantity connecting, which is the same, which remains identical to every observer that is moving, or if there was if there are many observers measuring the same particles, energy and momentum, they will all measure this distance mass to be identical. Mass is an invariant concept related. But we also know that P is E over C. That's our definition, if you want, of energy. That's also true. So I can start from here and say this will be minus E square over C square plus momentum square. Right? That's your invariant quantity, but that's equal to minus M square C square. Which tells us that energy is equal to M square C raised to 4. That's energy square plus P square C square. So energy and momentum are related this way, or better, often it is also written as E square. So the energy, square of energy minus the momentum square is equal to M square C raised to 4. right? Different ways of writing. This has this feature that E is equal to, if I am in the rest frame, you have E is equal to mc square. Like if you're in the rest frame, that has E is equal to mc square. And that is the relation we want to keep. E is not always equal to mc square. There is a momentum coming in. Whenever you write it in this form, it is often thought of as this is mass is dependent on velocity. So you can also define mass in that term, but that's not the way we are using it. For us, mass is invariant. Often in popular physics, when you write E is equal to mc square, m is not constant, it changes with velocity. So we don't want to, we really mean the rest mass. So this is actually the rest mass, and everywhere we are using it, that's the rest mass. But many times in elementary books or popular books, you want to avoid this complicated equation and you want to simplify that. So you would say that mass is changing with velocity. So there the mass is not the same if you want to have that the correct form. So that's your energy momentum. That is one thing we can do immediately. Next time we will come and talk about collisions and get some interesting result. But before that, let's do something. What if there is light moving? So if there is a photon, so photon is, maybe I should define at this stage. A photon is a particle associated with light. You can think of it as a wave packet, like confined, like you typically have light going as a monochromatic wave, right? So that you have electric field oscillating and it is moving in a certain direction. But let's say you have a wave packet, in a sense, this is like this. So the electric field is zero, and in long places, many places it is zero, but it is non-zero in a very finite region, and it could be moving with some velocity v. A photon is different from a monochromatic wave in the sense, what is the difference? It says that monochromatic wave has its velocity very fixed. Velocity means momentum. You know that it's going in a certain direction. So in that sense, it's a wave. But if you tell where is a monochromatic wave in this, we don't know. This is stretched out from minus infinity to plus infinity. So you don't know anything about the position of a monochromatic wave, but you know everything about the momentum. The opposite extreme is a wave packet. By a wave packet, I mean a photon. So this is the idea of a photon, is that it has a fixed position in the sense I can make this more and more compact, but not zero. I can make it more and more compact. But then if you ask what is its velocity, that's not a very good point to ask, right? Even though once you specify the position, its velocity is it has too much error, if you want to say, right? That's the idea of a photon. The photon is, you have it a compact form of energy electric field, but its velocity has too much error. It's not a good idea to ask what is the velocity. Exactly like here, it is not a good idea to ask where is its position. It's not well defined in principle. So same thing with the photon. Its momentum is not well defined, but its energy is very much well defined, at least directional. Okay, so that's your photon. What's the mass of a photon?
0.
Mass of a photon, you've come across?
Is 0.
0, correct, yeah. So mass of a photon is 0. So mass is equal to 0. So often we will say mass of gamma. So that shouldn't be confused with the Lorentz factor. Often a photon is given by the symbol gamma too. So that's equal to 0. Now, if we go back to our energy momentum relation and ask what's the connection between energy and momentum for a photon? And we learn that mass is equal to 0. So for a photon, only for a photon, no other particle satisfies this. E square is equal to p square. That means E is equal to momentum times C. The magnitude of the momentum. Let's see, let me put it this way. It's magnitude of the momentum times the speed of light is equal to energy. In fact, we will go one step further, and like this is quantum mechanics coming up, right? But photon is a quantum particle. You would say energy here is h bar omega. So if you know the frequency of light, if you want, then you can associate with that. But again, here we have actually gone into the wave packet description of light instead of a photon. So that is, we have gone from one quantity to the other. And momentum, P, would be h bar times the wave vector associated with photon. And then you get the relation that K or omega is equal to K times C, which is nothing but lambda times nu is equal to C. So if you want, these are our Fourier. So from this point on, I have gone into the Fourier transform quantities related. That's just to give you a connection. Next time we will use this relation for sure, but not the quantum features of this. We'll start with the idea that photon is having energy and momentum the same. That has this nice feature. So before, I'll take one more minute to finish. So this is a quiz. I think it's a good thought to put in a little on this. So let's say you have an electron and a positron. So this is electron is having a negative charge, and that is a positron, which is exactly an electron, except that its charge is positive. It has the same mass. Most of the properties are the same, except its charge is opposite. And let's say there are two particles that come in. So there is electron that comes in like this, and positron that comes in from the other side. Right? They come and collide with each other. Right? Or you can think of it as they come in the same place. Oh, I cannot, you guys cannot see that, right? Yeah, no. Okay. Now, positron is an antiparticle of electron, which means that if they come together, they can disappear. Right? Matter and antimatter can disappear. So this will disappear completely, and what will remain is energy, which is basically photon. So you have electron which has a mass, positron which has a mass. They come and collide with each other, they disappear, and they create energy, which is very much possible in general. In general, this is possible, but this particular process is not possible. And now the point is, first you say that, oh, that's possible, but then you say that, oh, that cannot be possible because of what I just now told. So argue, or the question for you is, why is this not possible? The basic principles that gets violated if you allow this process. So look it up and try to answer that. Just to say, it should be interesting to just read about that. And next time I'll come and do real examples of that kind. Talk about collisions and so on. Okay. That's all. Thank you.
Yeah.
Yes, Christian, you have a few minutes. Okay, I'm just going, okay, this time I have to make sure that I don't end it for both of us. Okay, leave meeting, not end meeting for all. Okay. Oh, but I had to assign. Oh, how do I stop this? Hold on.
Yeah, I could leave and just rejoin.
Give me a second. I think this should be. Yeah, I think I can stop the record. No, let's stop and come back. I think just to make sure. Yeah, okay.
Okay.
Just let's rejoin. Yeah.